With 14.2 isolation amplifiers. All right, now let's go and have a look what they tell us. What is an isolation amplifier? They say an isolation amplifier provides DC isolation between input and output. It is used for protection of human life or sensitive equipment in those applications where hazardous power line leakage or high voltage transients are possible. The principal areas of application are in the medical instrumentation, power plant instrumentation, industrial processing, and automated testing. All right, now we're going to look at the basic capacitor coupled isolation amplifier. All right, here are the simplified block diagram of a typical isolation amplifier. Few things I want to point out. You will look here. There I got a supply and there I got a supply. You can even see our earth are different. That means these two stages are completely isolated from one another, all right? And what do we use for the coupling or the isolation barrier? We use a capacitor, all right? But now I can ask you a question. You see here we've got an op-amp, we've got a modulator, we've got an oscillator. On the other side we've got a demodulator and op-amp. Can't we now only use a capacitor? If I use a capacitor on its own, will it work as isolation between two stages? Yes or no? No. Why? You say no. Why? No, you say no, then you must tell me why. What is a capacitor? It's two plates with a dielectric material in between, all right? That means, according to me, if I want to isolate two things and I use a capacitor there, it will work. But why do we do all everything to have two different supplies and to have a modulator and an oscillator and on the other side a demodulator? Why? Anybody? If we think about, they don't mention it in the book, but when is the plates the largest apart? For a small capacitance or large capacitance? Let's say if I want to build a capacitor, when will the plates be the furthest apart? For a small capacitance value or a high capacitance value? What are you saying? A high. What is the basic formula when you want to determine capacitance? Capacitance is equal to the area of the plate multiplied by a dielectric constant and all those things divided by the distance between the plates. All right. Now, if you tell me the closer the plates together, the higher the capacitance value. Exactly opposite that my clever students telling me in the class. Exactly opposite. That means if you want to have good isolation, you want your plates further apart. And that will be for a very small capacitance value. All right. That means that's why we do all this stuff here. I have a modulator and an oscillator and a demodulator and an oscillator to get the information across the plates. All right. Otherwise, you're going to have a large capacitance value, then your plates is going to be very close to one another. That means the higher the capacitance value, the smaller the distance between the plates. All right. All right. There they give us the basic thing. Again, I repeat, an op-amp, a modulator, oscillator. We got the capacitor for that. We can also use different types of couplings, demodulator, op-amp to get our information. Hey, inside here. All right. Then we can also get different types of isolation. We can use a transformer. Because a transformer, we can use a transformer coupling. What else? We can use optical coupling also. That means it's not only capacitor coupling, we can have transformer coupling, and we can have opto coupling to basically isolate our different stages. All right. Any questions? All right, here they show us what actually happens here. Again, we can make use of different type of modulation. In this case, they talk about pulse width modulation, all right? That means the way I modulate my signal. We can also look at amplitude modulation, all the different types of modulation. Got the isolation barrier. On the other side, we demodulate again. You see, here's my input signal. Here they talk about amplitude modulation. That's the way we modulate the signal. On the other side, we demodulate, and we will get basically our output signal there. Here's pulse width modulation. We can also make use of pulse width modulation. That's only the different types of modulation we can apply. All right. All right, here they're going to give us an example of decoupling. What's the meaning of decoupling? Let's have a look at the example. They say ISO-124 is an integrated circuit isolation amplifier. It has voltage gain of 1 and operates on positive and negative DC supply voltages for both stages. This device uses pulse width modulation, sometimes called duty cycle modulation, with a frequency of 500 kilohertz. It is recommended that the supply voltage be decoupled with external capacitors to reduce noise. Sometimes show the appropriate connections. All right, now what the manufacturer specify, they say the solution. The manufacturer recommends a 1 microfarad tantalum capacitor for low leakage from each DC supply pin to ground. This is shown in figure 14.13, where the supply voltage are plus minus 15 volts. And here's the solution to that, for that decoupling of my supply voltages. They say we use 1 microfarad tantalum capacitors. Now on my input side, you will notice I will take from my ground, or my ground, a capacitor to my negative and 1 to my positive supply. A 1 microfarad tantalum capacitor on the one side. We do exactly the same on the other side, right? And if there's high voltage spikes coming through, the capacitor will basically block those spikes. The next one, the next isolation amplifier. Here we're going to look at the transformer coupled isolation amplifier. The first one was capacitively coupled. This one with the dotted lines here indicates a transformer coupled isolation amplifier. They will give us the information about this. They say the Texas Instruments Burr Brown. Texas Instruments is the manufacturer of the IC. The number is a 3656 kg. Is an example of an isolation amplifier that uses transformer coupling to isolate the two stages. They say, unlike the ISO-124, which has a fixed unity gain, the 3656 kg provides for an external gain adjustment of both stages. A diagram of the 3656 kg with external gain resistors and coupling capacitors is shown in figure 14.14. All right. Here they show us our external gain resistors. Here there's RF1 and RIN1, and on the other side I have RIN2 and RF2. That means by varying those resistors, I can vary the gain of my isolation amplifier. That means this thing won't have a fixed gain. Here they give us the formulas for that. They say the voltage gain of both input stage and output stage can be set with external resistors connected as shown in figure. The gain of the input stage is AV1 is RF1 divided by Rin1 plus 1 for the output stage. AV2 is RF2 divided by Rin2 plus 1. My total gain will be AV1 times AV2. All right. Let's have a look at the example. Example 14.4, they say determine the total voltage gain of the 3656 kg isolation amplifier in figure 14.15. All right, they give us the resistor values is given here. RF1 is 22K, Rn1 is equal to 2,2 kilo ohms. That means that will give me 10 plus 1, it will give me a gain of 11 for my first stage. AV2, if we look at AV2, RF2 is a 47K and Rin2 is a 10K. That means that will give me 47K divided by 10K will give me 4,7 plus 1. That will give me 5,7. That means my overall gain or my total gain will be AV1 times AV2, and that will give me 62.7. All right. Any questions? All right, applications. Where do we use isolation amplifiers? In this case, that is basically in the medical field, where we basically can, if they want to measure the heartbeat of a fetus, then they will have normally 2 electrodes. Or even if they want to measure your heartbeat, they will have 2 electrodes. They will also have a shielded cable, and that will go to my isolation amplifier. Why? Because sometimes they got big screens. If you think about the old stuff, the old screens, they had a very high voltage on the screen. And if something goes wrong, it's not necessarily something will go wrong, that high voltage can come to the patient and kill him, because then you will have high voltage on the electrodes, and these things make very good contact in your skin. Otherwise, they won't pick up very small signals, all right? And that can cause problems. And that's why they use an isolation amplifier. On the input side will be a low voltage side with different supplies, all right? That input side will have its own supply, that will also have its own supply, and that's just to protect human life if you use these instruments, all right? That's one application of that, where they want to measure the heartbeat of a fetus. Any questions? Any questions? All right, that's basically all for the isolation amplifiers. The next part, 14.3, we basically now finished with 14.2. We're going to look at 14.3, the operational transconductance amplifier, OTAs. Now, what is an OTA? What does it do? It's an amplifier, all right? And you'll notice here, we got here 2 circles. What does that normally indicate? What does those 2 circles indicate? Sometimes you get a circle with an arrow in. What does that indicate? What does that indicate? Huh? A transformer. Hey, are you sure? Are you sure it's a transformer? That indicates a current source, all right. Not a transformer, a current source. All right, they say conventional op-amps are, as you know, a primary voltage amplifier. All right, it's a primary voltage amplifier. Op-amps normally amplifies voltage, all right. Which output voltage equals the gain times the input voltage. That means you put an input voltage, you amplify, you will get a certain output voltage, normally a few times larger than the input, all right. They say the operational transconductance amplifier, OTA, is primarily a voltage to current amplifier. That means my input is voltage, my output is a current, in which the output current equals the gain times the input voltage. All right, that's actually a voltage to current amplifier. That is a OTA. Now let's have a look at the symbol of OTA. All right, here's a symbol of OTA. Looks like an op amp with the two circles there in front. And there they show us a bias. All right, by varying the bias current, I can also vary the gain of the amplifier. But that is the symbol of OTA. Now, conductance. What is conductance? What is conductance? And what is the unit of conductance? You S3 students, or maybe S4, but I ask you very simple questions, you can't even answer that.
1 over impedance.
What?
1 over impedance.
All right. Siemens. But what is that actually? The inverse of resistance or the inverse of impedance. All right. Because when I calculate the resistance or impedance, how do I normally calculate? Voltage divided by current. What is this? Current divided by voltage. It's the inverse. All right. The unit is Siemens. All right. Are you with me? All right, they say in OTA the transconductance is depending on a constant K times the bias current. I bias is indicated in figure 14.6. The value of the constants depending on the internal circuit design. All right, this K value will be determined by the circuit design. And that will normally be supplied where? The manufacturer. That means the manufacturer will tell you for this device, the K value is that. All right. And they say the output current is controlled by the input voltage and the bias current as shown by the following formula. I out is equal to GM times V in. All right, we get that from that. Is equal to K times I bias times V in. That is my current. Now they say transconductance is a function of the bias current. Right, now we're going to look at that constant value. They say the relationship of the transconductance and the bias current in OTA is an important characteristic. The graph in figure 14.18 illustrates a typical relationship. Notice that notice that the transconductance increase linearly with the bias current. The constant is proportionally is the slope of the line. In the case, K is approximately 16 microsiemens per microamp. 16 microsiemens per microamp. You can see as my bias current increases, my transconductance also increase linearly. All right. Larger bias currents, larger transconductance. All right, straight line. And here they give us for that a value of around about 16 microsiemens per microamp. All right, that is my constant value. Let's have a look at the example. They say if an OTA has a GM of 1,000 microsiemens, what is the output current when the input voltage is 25 millivolts? They give us the input voltage, they give us GM, then I can calculate my current, and I can say I out is equal to GM times V in is equal to 1,000 microsiemens times 25 millivolts, and that will give me 25 microamps. All right, please take note, also in the exams and tests, if you don't give me the units, if you don't tell me it's 16 microsiemens per microamp, what will I do? I will mark it wrong. So that means that's your choice. All right. If you don't give me information, I can't read it, I mark wrong.
But here, I think macro, they can cancel each other. So I can just say S per ampere. Because it's macro over micro.
Depends what I ask you, all right? All right, let's have a look at basic OTA circuits, all right? All right, they say figure 14.19 shows the OTA used as an inverting amplifier with a fixed voltage gain. The voltage gain is set by the transconductance and the load resistance as follows. Now they say divide both sides by V in, and V in and divided by V out divided by V in is equal to I out divided by V in times RL. Because the output divided by the input will give me what? Output voltage divided by input voltage will give us gain, all right? Here they showed to us, why do they tell us this thing got a fixed gain? Why can I say this thing got a fixed gain? How do I vary the gain of an OTA? How do I vary the gain of an OTA? What do I vary to vary the gain? By varying my bias current. By varying my bias current, I can vary the gain of the OTA. Why do they say it's a fixed gain? Because I got a fixed bias current. You with me? Just remember, by varying the bias current, you can vary the gain. All right. You with me? And there you can see what I already told you. The output voltage divided by input voltage give me the gain. They say since V out over V in is the voltage gain, and I out divided by V in is GM, then I can say the voltage gain is equal to GM times RL. Now if we have a look at this, they say voltage gain is controlled by this variable resistor. If I vary the resistor, what will I vary? I will vary my bias current. If I vary my bias current, what do? I vary my gain. Here they say voltage gain is controlled by this variable voltage. Here they make the voltage variable. You will also vary the bias current. You will vary the gain. You with me? All right, now we're going to look again at the specific OTA. That means OTA you can go and buy with a certain number. Here they state the LM13700 is a typical OTA and serves as a representative device. The LM13700 is a dual device package containing two OTAs and buffer circuits. Figure 14.21 shows the pin configuration using a single OTA in the package. The maximum DC supply voltage are plus minus 18 volts, and the transconductance characteristics happens to be the same as indicated by the graph in figure 14.18. For an LM13700, the bias current is determined by the following formula. All right, now you must listen to me, eh? You must listen to me nicely. They say I bias is plus V bias minus V minus 1.4. Some of the old books, some of the examples in the books, they use 0.7 there. If you're going to use 0.7 in the test or in the exam, what will I do? I will mark you wrong. That's why I'm telling you nicely in class. Now I'm going to repeat it. Don't use 0.7 there. You can use 0.7, that's your choice. But it's my choice to decide if I'm going to mark it right or wrong. You with me? That's why I repeat it. I don't want you to do things wrongly. You must do it correctly. All right. But here they also tell us, they say, the 1.4 volt is due to the internal circuit where the base emitter junction and the diode connected the external R bias with a negative supply voltage. The positive bias voltage plus V bias may be obtained from the positive supply voltage. That means you got a junction there and you got a diode. That means the junction will give you 0.7, the diode will give you 0.7. 0.7 plus 0.7 will give me 1.4. All right. Everybody happy? All right, here they show it's a dual package. For the first one, it will be, one input will be 4, the other one will be 3. The supply is going to be the same. That'll be, I bias will be pin 1, and the output will be pin 5 for the first IC. For the second one, it will be 13 and 14, and 16 and 12. All right. The supply is the same because it's in the same package. They got the same supply. All right. Any questions? Any questions? No questions. All right, they say, note, not only does the transconductance in the OTA vary with the bias current, but so do the input and output resistances. Both the input and output resistance decrease as the bias current increases. All right. You can see if my bias current increase, the resistances decrease. All right. It's also linear, the input resistance and the output resistance. Let's go and have a look at example 14.6. They say in the OTA in figure 14.23 is connected as an inverted fixed gain amplifier where plus V bias equal to plus V determine the approximate voltage gain. All right, this thing will also have a fixed voltage gain because my bias current is fixed. It's not going to change. And first of all, we calculate I bias. It's plus V bias minus V minus 1.4. It's 9 minus 9. That will give me a positive voltage. Minus 1.4. When I work that out, I will get a bias current that's 503 microamps. All right. Now, they say using the same constant value, we will normally use this constant value, 16 microsiemens per microamp from the graph. And when we work our GM is K times I bias, so we already got the bias current as 503, and that will give me 8,05 times 10 to the power 3 microsiemens. You can also go and say, I can make it 8,05, what? Millisiemens, all right. But it's better if you use micros, work in micros. But you can, if you give me 8,05 millisiemens, it's going to be exactly the same, all right. Because micro is 10 to the power minus 6, a milli is 10 to the, that's actually kilo. And then it will give me actually 10 to the power minus 3 at the end, all right. They say using the value of GM to calculate the voltage gain, AV is GM times RL, and that will give me a voltage gain of 80,5. Everybody happy? All right. If you're happy, I'm happy. Let's move on. All right, here we're going to look at OTA applications. For what can we use the OTA? In this case, we use the OTA as an amplitude modulator. That means here if we go and look at the modulator, we will have normally your carrier frequency will be a high frequency, and then you will normally modulate the information that's a much lower frequency on top of it. You see here should actually be my carrier signal. It's going to be a high frequency at the input. That means if I only put that and I keep that constant, what will I have out? I will have a constant high frequency out, all right? But now, by applying this low frequency or this modulated signal on top of it, what will happen? It will modulate that signal, all right? Because here I will have low gain, and as that increases, what will happen to the gain? It will increase. And there the gain will decrease again, all right? Because by varying the bias current, I vary the gain. All right. That is an amplitude modulator. Here you can see the same formula apply. V modulated minus V minus 1.4, not 0,7. Let's have a look at this example, a practical example. They say the input to an OTA amplitude modulator in figure 14.25 is a 50 millivolts peak to peak 1 megahertz sine wave. All right. 50 millivolts, 1 megahertz, the peak to peak value. Determine the output signal given the modulator voltage shown is applied to the bias input. All right. Here's my modulated signal. It goes from a certain voltage to 10 volt maximum to plus 1 volt minimum. Frequency 1 kilohertz. All right. First of all, they say the maximum voltage gain is when I bias and GM is maximum. This occurs at the peak of the modulating voltage. What's the peak of the modulating voltage? 10 volts, all right. That means the modulating voltage maximum is 10 minus 9 minus 1.4 divided by my bias resistance is 56 kilo ohms, and that will give me a bias current of 314 microamps, all right. All right, from the graph in figure 14.18, with the constant K is approximately 60 microsiemens per microamp. We use the same constant. And then I can calculate GM. GM is K times I bias, and that will give me 5,02 millisiemens. Then I can calculate my voltage gain maximum, and that is equal to my GM value times RL. RL was 10 kilo ohms, and that will give me 50,2. Then my output maximum will be basically the gain times my voltage, and that will give me 2.51 volts. All right. That is now for the maximum value. Then we must go and do exactly the same for the minimum value. And that the minimum value is V modulating minimum minus V minus 1.4. Now the minimum voltage, if you remember, was 1 volt positive. Is 1 minus 9 minus 1.4 divided by the 56 kilo ohm, and that will give me 154 microamps. All right. Now I calculate GM for that bias current, and that will give me 2,46 millisiemens. All right. Then I can calculate AV minimum, it's GM times RL. That will give me 24,6 gain, and then I can calculate V out minimum, and that will give me 1,23 volts. All right, that means my maximum was 2.51, and my minimum is 1.23. You can see here, here's my maximum 2.51, my minimum is 1.23, and there's my modulated signal. All right. This frequency here will be, what, 1 megahertz. All right, that was the input or my carrier frequency. Any questions? Any questions? All right, let's finish this part. The last part is the Schmidt trigger. That's also basically what? What do we have here? We have basically an OTA, and this will give me what? That will give me a positive voltage. That will actually give me also a little bit of hysteresis. It will determine a certain trigger point because it will actually determine this voltage with my input voltage. All right. Now let's quickly have a look how this thing is going to work. I will also have a fixed gain. We have a look here. We're going to have two trigger points. If my output is positive, then I will have a positive voltage across here. All right. That will give me a certain voltage. That means my input signal, this input signal, must go above that point. When it reaches that point, what happens then? Then this becomes more positive. What will happen to the output? It works like a comparator. When that becomes more positive than this voltage across R1, what will happen to the output? It will go negative, right? But now you must remember what will happen to this voltage now. The output is negative. This voltage is also going to be negative, all right? And then it will stay negative for the whole time. At this point, my input signal becomes more negative than that voltage. When it becomes more negative, what happens then? Output will go positive, all right? You with me? All right, very simple. But you must remember the output is positive, the voltage here is going to be positive. This input signal must go more positive or become more positive. When it becomes more positive, the output will go negative. And for that whole duration of time, it will stay negative. But here, my input signal becomes more negative than the voltage across R1. What happens then? It will go positive again. Any questions? All right, that'll be all for today.